Okay, so probably reinforce your chapter 6 knowledge if you're watching this or doing this work for chapter 7. This is all stuff we know already. We've done this in grade 11, we've done this in chapter 6. It's just kind of writing it down so we can see it. But I have diagrams to kind of show you why we know it already. So let's talk about sine versus cos for the first time. First of all, we're talking about equivalent trig functions. So eventually we're going to need to flip from one trig function to another because it's either going to help us or it's more simple or whatever the case may be. Knowing that something is equivalent is the first step to moving to an equivalent function, which will be necessary when things get complicated. So let's recall sine x versus cos x. Here's a graph. I just graphed sine x being at the origin for right now. And I wrote down one equation. This represents negative sine x. It starts at the c value and it's going down. And I'm just going to come up with three more functions like we've done many times in chapter 6. So for instance, my second function, I'm going to just pick a random point over here. I'm going to start over here. This is where positive sine starts, and it's shifted pi to the left. So I can come up with a positive sine function that's shifted pi to the left. And these are equivalent trig functions. We know this already based on the period, or a quarter of the period, or a half of the period. I'm going to look at number 3. That's where cos starts at pi over 2 to the left. So I can represent this using cos, but it's going to go to the left, pi over 2. And lastly, number 4, my last one is going to be a cos function, but a negative cos function, and that's shifted pi over 2 to the right. Okay, so nothing new here, but it's pretty important to see from here that we can navigate our way back to something more simple, which is negative sine of theta, right? There's no phase shift in negative sine theta, which is why in chapter 6, I'm like, if you're going to pick a phase shift, make sure it's around the y-axis, as close as possible. If you could pick a phase shift on the y-axis, 100% of the time, pick that phase shift, because it's 0. Okay, just like we like to plug in zeros, we like zeros in phase shifts as well. Okay, so eventually in chapter 7, later in chapter 7, you're going to have to maybe understand that one of these, that you don't know what's going on here, is just the same as this. And then now it's easy. Okay, and that's probably the hardest part of chapter 7 in one sentence. Okay, let's bring it back to chapter 1, even versus odd functions. So again, I'm just doing 4 different types of equivalent functions and why they're equivalent based on information we already know. Even and odd functions, remember this formula, f at negative x equals f at x. A parabola is even because it's symmetrical around the y-axis. If I plug in a negative 4, it's the same as plugging in a positive 4, right? They're both positive 16. So that's how I remember the formula for even functions. I just base it on a parabola. Well, we know cos is symmetrical around the y-axis, right? Cos starts at the max. It's not phase shifted. There's no shift. Just cos is symmetrical. So it's an even function, which makes this true. So if I ever have a negative angle in my cos function, I could just say it doesn't exist. It doesn't matter. What's the point of having a negative angle? It's the same thing. So something that might be a little confusing, I could just eliminate. And eliminating something, for the most part, is probably simpler. Okay, so going from here to here, these are equivalent because of an even function. Likewise, I know we don't really understand tan being odd, but let's not worry about that right now. Let's talk about sine. Sine starts here and has rotational symmetry around the origin, right? Which makes it odd. But algebraically, if I plug in a negative x into the function, I should get a negative version of the function. And this is true with sine. You can see the rotational symmetry because the middle is at the origin. So if I have a negative angle, I much rather have a negative outside the function for life. I'd rather have that. Because there's a chance that there's a negative sitting outside here somewhere that I'm going to combine with that negative. Negatives are gone and things are going to work out beautifully. Okay, but a negative inside here, can't really do much. Okay, I don't like stuff inside the angle. You're going to see where it comes more of a pain later on in the chapter. A lot more things occur inside. Okay, so you can think of this as an identity. 2 more identities, 4 more identities, right? But there's an infinite number that you can make over here. This is just within one period. There's 4 of them. Okay, and this is going to lead us into identities in this chapter, which, grade 11, you might have had 12. There's honestly an infinite number of identities. I don't memorize them. I just know situations, and I consider myself pretty good at identities, and I don't memorize stuff. So let's talk about our 3 quadrants that are not quadrant 1. So if I have an angle in any of the 3 quadrants that are not quadrant 1, I can come up with an equivalent trig function to put it back in that quadrant. We know this already, right? The related acute angle. We've done this all in chapter 6. So if I have an angle down here, no matter if it's sine, cos, or tan, this is going to be 2 pi minus the related acute angle, 2 pi minus theta, no matter what, if it's down here. This is going to be the same thing as saying, well, that's the same thing as just saying negative sine theta, because sine is negative here. And that's what the related acute angle does for us. Cos is positive here, tan is, tan is negative. Okay, cos is positive, it's on the right side of the y-axis, and tan is negative. Just a reminder for cast. I'll just do it on the first one. Again, these, maybe don't look so complicated. To me, they do. This is way simpler. I see this, I say, nope, absolutely not. That's the same thing as this. I'd rather use the one that has fewer characters. Likewise, when I have pi plus theta, okay, in this quadrant, pi plus theta, okay, sine is negative here because we're below the x-axis. Cos is negative because we're to the left of the y-axis. And tan is positive because tan is positive here. The slope of that tangent is positive, and or sine over cos is positive, whatever one of the 3 ways you want to know that. Okay, whether you're using cast or geometric visual interpretation, whatever you want. Last one, this quadrant, pi minus theta, pi minus theta. We know that sine is positive here, cos is negative, and tan is negative. Okay, I'm not going to spend too much time here because we know this stuff already. Okay, the problem is, guys, when we see this with no other context, we're less likely to understand that it switches to this. When we're doing questions that have to do with related acute angles, yeah, we're in that mode where it's easy for us to do. But then sometimes you're going to see this and you're going to be like, well, what do I do with that? Well, if you change it to this, you might see more. Okay, but that's a later thing. Okay, last one. This one you don't know. You kind of know, but you just never really put it down into words. A right angle triangle. When you have an angle and a right angle, the other angle is always just 90 degrees minus this angle, right? Because they have to equal 180. And if you're taking away a 90, these have to split another 90. And if you know one angle, 90 minus that angle gives you the third angle. Easy. What's more important is I hope you've realized doing trig over the years that sine of this angle is the same as cos of this angle. Let's see why. If this is the hypotenuse, and I'm talking about theta, this is the adjacent, and this is the opposite. Sine theta is O over H. Cos of this angle, now I'm talking about cos, this becomes A, because it's the adjacent. Cos of this angle is adjacent over hypotenuse, and that's the same ratio. So sine of this is always cos of 90 minus the other angle, or pi over 2 minus the other angle. So we can quantify that and say, well, that's the same as cos of pi over 2 minus theta. Is that the same as this? No, it's a different kind of way to understand equivalent trig functions. This is based on our knowledge of quarter of the period, and this is based on a 90-degree triangle, right? They look similar. Maybe if you factor something out, they could be similar if it's an even function, but we're just creating based on knowledge. Cos of theta is the same as sine of the opposite, same way. And tan of theta, take a look at tan. Let me erase these guys. If tan of theta is OA, what could be AO? Cotangent, right? That's the only way I can come up with another function. And yeah, the same could be true for sine with cosecant and cos with secant. Sure. Okay. Again, there's many more that we can create, possibly infinite, but we want a basis to start, at least for trig identities. Okay, 7.1 is pretty easy, and it'll definitely help with 6.